The Derating factor for RHO equals 120 compared to RHO equals 90 can be approximated as 0.85. This derivation utilizes figure B 310.1 in the National Electrical Code and the interpolation method outlined in Article B 310.15b7. The steps are as follows. Firstly, locate the point on the interpolation chart corresponding to RHO equals 90 and a temperature rating of 75 degrees Celsius. This temperature rating is assumed for National Electrical Code tables 310.77 through 310.86. Secondly, draw a line from this point parallel to the RHO equals 90 line. Thirdly, determine the RHO value corresponding to the point where this line intersects the RHO equals 120 line. Fourthly, the RHO value found in the third step represents the approximate Derating factor. Let's go through an example calculation. Starting with RHO equals 90 and a temperature rating of 75 degrees Celsius, the interpolation chart in figure B 310.1 yields an approximate RHO value of 110 for RHO equals 120. Therefore, the Derating factor is calculated as 110 divided by 90, which equals approximately 0.85. For application to convert the ampacities listed in tables 310.77 through 310.86 for RHO equals 90 to RHO equals 120, simply multiply the original ampacity by the Derating factor of 0.85. For example, if an ampacity of 20 amps is listed in table 310.77 for RHO equals 90, the ampacity for RHO equals 120 would be 20 amps multiplied by 0.85, which equals 17 amps. Soil resistivity, denoted by RHO, is a critical factor in determining the ampacity of underground electrical conductors. The higher the soil resistivity, the lower the ability of the soil to dissipate heat generated by the conductors. This necessitates derating the ampacity of the conductors to prevent overheating and potential damage. The National Electrical Code provides tables and guidelines to adjust ampacity based on soil resistivity values. Tables 310.77 through 310.86 specifically address underground conductors and are based on a soil resistivity of RHO equals 90. When the actual soil resistivity is higher than 90, a Derating factor must be applied. Figure B 310.1 in the National Electrical Code provides an interpolation chart that allows for the determination of Derating factors based on different soil resistivity values and conductor temperature ratings. Article B 310.15b7 outlines the methodology for using this interpolation chart. The process involves locating the point on the chart corresponding to the known soil resistivity and temperature rating, then drawing a line to determine the corresponding value for the desired soil resistivity. This value is then used to calculate the Derating factor. The temperature rating of the conductor is crucial in this calculation. Tables 310.77 through 310.86 are typically based on a conductor temperature rating of 75 degrees Celsius. However, if the conductor has a different temperature rating, the interpolation chart must be used accordingly. The Derating factor is a multiplier that is applied to the ampacity value listed in the tables. This adjusted ampacity represents the maximum current that the conductor can safely carry under the given soil resistivity conditions. It is essential to accurately determine the soil resistivity at the installation site to ensure the correct Derating factor is applied. Soil resistivity can be measured using specialized equipment and techniques. Consulting with a qualified electrical engineer or electrician is recommended to ensure accurate measurements and proper application of the National Electrical Code guidelines. Ignoring soil resistivity and failing to derate ampacity can lead to conductor overheating, insulation degradation, and potentially electrical failures or fires. Therefore, it is crucial to adhere to the National Electrical Code requirements and best practices for underground electrical installations. The Derating factor of 0.85 is an approximation for RHO equals 120 when compared to RHO equals 90. For more precise calculations, especially in critical applications, it is recommended to consult the National Electrical Code and perform a detailed analysis using Figure B 310.1. The National Electrical Code provides a comprehensive set of rules and guidelines for electrical installations to ensure safety and prevent hazards. Understanding and applying these guidelines is essential for all electrical professionals and anyone involved in electrical work. The ampacity of a conductor is the maximum current it can carry continuously under specified conditions of use without exceeding its temperature rating. Several factors influence ampacity, including conductor size, insulation type, ambient temperature, and soil resistivity for underground installations. Derating is the process of reducing the ampacity of a conductor to account for conditions that reduce its heat dissipation capability. This ensures that the conductor operates within its temperature rating and prevents overheating. The National Electrical Code tables provide ampacity values for various conductor types and sizes under specific conditions. These tables are based on certain assumptions, such as ambient temperature and soil resistivity. When these conditions deviate from the assumptions, derating factors must be applied. Soil resistivity is a measure of the soil's resistance to the flow of electrical current. High soil resistivity reduces the soil's ability to dissipate heat, which can lead to conductor overheating. The National Electrical Code requires that the ampacity of underground conductors be derated based on soil resistivity. Figure B 310.1 in the National Electrical Code provides an interpolation chart for determining derating factors based on soil resistivity and conductor temperature rating. This chart allows for a more precise adjustment of ampacity than using a single derating factor. The interpolation method outlined in Article B 310.13b7 provides a step-by-step process for using Figure B 310.1 to determine the derating factor. This method involves locating the point on the chart corresponding to the known soil resistivity and temperature rating, drawing a line to determine the corresponding value for the desired soil resistivity, and then calculating the derating factor. The derating factor is typically expressed as a decimal value between 0 and 1. This value is multiplied by the ampacity listed in the National Electrical Code tables to obtain the adjusted ampacity for the specific conditions. It is important to note that the derating factor is not a fixed value and can vary depending on the soil resistivity and conductor temperature rating. Therefore, it is essential to use the interpolation chart or other appropriate methods to determine the correct derating factor for each installation. In addition to soil resistivity, other factors can also affect the ampacity of underground conductors, such as ambient temperature and the number of conductors in a raceway or cable. The National Electrical Code provides additional derating factors for these conditions. It is crucial to consider all applicable derating factors when determining the ampacity of underground conductors to ensure safe and reliable operation. The use of appropriate software or calculation tools can simplify the process of determining ampacity and applying derating factors. These tools can also help to ensure that all applicable codes and standards are met. Consulting with a qualified electrical engineer or electrician is recommended for complex installations or when there is uncertainty about the correct ampacity and derating factors. The proper installation of underground conductors is also essential for ensuring their safe and reliable operation. This includes proper trenching, backfilling, and compaction of the soil. The conductors should be installed in accordance with the National Electrical Code and manufacturer's instructions. Regular inspection and maintenance of underground electrical systems can help to identify and prevent potential problems. This includes checking for signs of corrosion, damage, or overheating. Promptly addressing any issues can help to extend the life of the system and prevent costly repairs. Understanding and applying the National Electrical Code requirements for ampacity and derating of underground conductors is crucial for ensuring the safety and reliability of electrical systems. By following these guidelines and best practices, electrical professionals can help to prevent electrical hazards and ensure the safe operation of electrical equipment. Remember that the 0.85 derating factor is an approximation. More accurate calculations may be required for critical applications, and consulting the NEC and qualified professionals is always advisable. Considering other factors like ambient temperature and the number of conductors bundled together is also important for a comprehensive ampacity calculation. When dealing with underground conductors, it's also vital to ensure proper installation techniques, including correct trench depth, backfill material, and compaction to facilitate heat dissipation. Regular inspections and maintenance of underground systems can help identify potential issues early on, preventing costly repairs and ensuring long-term reliability. Staying updated with the latest NEC revisions is also crucial, as codes and standards can change to reflect new technologies and safety practices. These revisions may introduce new derating factors, calculation methods, or installation requirements that need to be adhered to. Using appropriate software or calculation tools can greatly simplify the process of determining ampacity and applying the necessary derating factors. These tools often incorporate the latest NEC tables and allow for easy input of various parameters such as soil resistivity, ambient temperature, and conductor characteristics. This reduces the risk of errors and ensures that the calculations are accurate and compliant. Ultimately, ensuring the safety and reliability of electrical systems requires a thorough understanding of the NEC, careful attention to detail, and the use of appropriate tools and techniques. Consulting with qualified professionals and staying up to date with the latest industry standards are essential for maintaining a safe and efficient electrical infrastructure. While the approximated derating factor of 0.85 provides a quick estimate, remember to consider the specific application and consult the NEC for a more precise determination, especially when dealing with high current circuits or critical loads. Employing a more detailed analysis will enhance the accuracy and safety of your electrical design. Remember to consult local codes and regulations, as they may have additional requirements or restrictions that need to be considered in addition to the NEC. Also remember to maintain detailed records of all calculations, derating factors, and installation details for future reference and troubleshooting. These records can be invaluable for identifying potential problems and ensuring that the system continues to operate safely and reliably over time. Finally, remember that electrical work can be dangerous, and it's always best to consult with a qualified professional if you have any questions or concerns. Working with electricity requires specialized knowledge and skills, and it's important to prioritize safety above all else. By following these guidelines and best practices, you can help to ensure the safe and reliable operation of electrical systems and prevent electrical hazards. Remember to also consider the long-term effects of soil conditions on the performance of underground conductors. Soil moisture content, chemical composition, and other factors can change over time, which could affect soil resistivity and the conductor's ability to dissipate heat. Regular monitoring of soil conditions and periodic inspections of the electrical system can help to identify any potential problems and ensure that the system continues to operate safely and reliably. When selecting conductors for underground installations, it's also important to consider the insulation type and its suitability for direct burial. Some insulation types are more resistant to moisture, chemicals, and other environmental factors than others. Choosing the right insulation type can help to extend the life of the conductor and prevent premature failure. Remember, the information provided is for general guidance only and should not be considered a substitute for professional advice. Always consult with a qualified electrical engineer or electrician before undertaking any electrical work. The use of appropriate personal protective equipment, such as gloves, safety glasses, and insulated tools, is essential when working with electricity. Always to energize circuits before working on them and follow lockout/tagout procedures to prevent accidental re-energization. Remember that safety is paramount, and it's always better to be cautious than to take unnecessary risks.